All right, happy Tuesday, everyone. I don't know if you've heard, but 6 weeks from this very day is Sandwich Day. Oh, and it's also Election Day. But that's 6 weeks from now. Today is National Voter Registration Day, so if you haven't already, make sure you register and have your voice heard on a litany of ballot choices. And speaking of today, we're discussing a topic that we haven't touched on in a couple of years, and that's the benefits of radiant floor heating systems. They bring greater comfort, short-term and long-term efficiencies, and indoor environmental quality benefits, such as cleaner air, reduced noise, and improved human thermal comfort to our homes. And it's that latter point that is in high demand right now. Today's presenter is in a rare club because he's making his 4th appearance on the webinar series. Steve Swanson is the national trainer at Uponor North America, providing training at the factory and around the nation to contractors and installers on radiant heating and cooling, hydronics, and commercial plumbing. He has 47 years of experience in hydronic heating and plumbing. Now, for 20 of those years, he was the vice president of a plumbing and heating supply company in the Twin Cities and gave seminars for hydronic heating and plumbing around the country. In addition, for 15 years, he taught the state of Minnesota boiler certification licensing. Now, Steve is a licensed CEU instructor for the states of Michigan, Minnesota, Florida, and Washington. He is also on the board of advisors for the Radiant Professionals Alliance and an ASSE certified hydronics trainer. Now, today's webinar is being brought to you by Uponor. And during the course of today's presentation, you could submit questions for our guest. Simply use the questions box on the right side of your screen. I'll review those questions and pose them to Steve during the Q&A time set aside after his presentation. Steve, welcome back to the webinar series.
Well, thank you, Mike. Thank you, Mary. Thank you for having me back again. It's always a pleasure to come and spend time with all of you folks today talking about a subject that's passionate to my heart, radiant heating. And we are in the coronavirus time of our lives right now, and I'm presenting this from my office at home. And I just want to say that because we have a 2-year-old granddaughter who's staying here. My wife is watching her, and she just learned how to open doorknobs. So we may have a guest, and you'll enjoy meeting her. She's a lovely girl. So let's get started with what we want to do today, what we're trying to accomplish. So what we'd like to do is, first of all, to understand indoor environment quality. We're going to start off with just a really high-level view of radiant floor heating systems. We want to talk about the efficiencies of these heating systems, how they tie together with human thermal comfort, and how radiant heating improves the indoor environment of our homes. This is a big issue these days. Houses are getting tighter and tighter all the time, and they lock up contaminants inside of our house. So how do we take care of that? How important is temperature to comfort? What is indoor environment quality anyway? And then how does radiant help a home's air quality? So we'll start off with just a very quick overview of radiant heating by itself. Oops. All heat flows from hot to cold. It cannot not do that. It has to do that. It's a form of energy, heat is, that comes in one of 3 ways: conduction, convection, or radiation. Conduction is by touch. Convection is like I heat the air and the air heats you, or I heat a water and the water heats you. And radiation is by electromagnetic waves transmitted from the heat source to where the heat is going to be going. A perfect example of this is the sun's relationship to the earth. Although we're 93 million miles away, this radiated heat from the sun travels in space at -400 degrees Fahrenheit and doesn't give up any of its energy until it hits a surface. So understanding electromagnetic waves is one of the things to understand is there's no temperature in the electromagnetic waves, only energy. In order for the energy to be converted to heat, they travel through a transparent space until they hit an opaque surface where they are absorbed. The absorption of the energy increases the molecular action on the surface, which raises the temperature of the surface, and through conduction, heats the underlying mass. Now, you've felt radiant heating if you've ever been at a campfire on a cold night. You remember that the front of you feels warm, even though the outside temperature is very cold. And that's exactly what radiant heating is doing. It goes through the air and doesn't give up any energy. As soon as it strikes you, it gives up all of its energy and it's absorbed into you where it becomes heat. In a home, how does radiant heat in a home work? Very simply. Water is transmitted through the tubes buried in the cement. Usually this is 1/2-inch PEX pipe, 12 inches on center, and that heated water heats the cement around it. You could see this cement right here. So this is 1/2-inch pipe, 1/2-inch pipe, 12 inches on center right here, and it heats up this giant mass of concrete. As it heats this up, that concrete then begins to work its way up to the surface. And again, once it reaches the surface, it transforms into radiant heat and starts, so the entire surface is a heat emitter. Now what that means is instead of let's say, if you remember radiators from back, well, you might not, you may have seen one, where all that heat is in a little space. They're very, very hot to the touch. But because this heat emitter covers the entire floor, we can drop that supply water temperature incredibly low because we don't need very much per square foot of heating surface to do that. And that's one of the benefits of why radiant heating is so efficient. So how do we install, what are the installation methods? What possible ways can we install radiant? The good news is whether it's new construction or remodeling, there are ways to do radiant heating in nearly every conceivable application. Probably the most popular one that you've seen is the radiant floor, where it goes in the slab. And so the tubing is laid in the concrete, typically 4 to 6 inches of concrete. Now, 1,000 square foot basement with 4 inches of concrete weighs about 49,000 pounds, or about 25 tons. That's a huge amount of mass. So this is a very high mass, slow responding, very even form of radiant heat. And of course, this is for new construction. Now, the benefits of this is it's very even, very consistent heat. And when it's installed at construction, it's also the least expensive installation method. Again, it's not particularly cost effective for remodel jobs. There's a better way to do it. Nobody wants to bust up their basement. Now, just as a note though, it's best not to use setback thermostats on a slab system, on a high mass slab system, since it takes so long to recover. Now, moving on from there, we have gypsum or gypcrete overpours. Now, this is gypcrete is comes out soupy and dries hard within an hour. And it's a lightweight plasticized concrete. It typically weighs about 10 to 14 pounds per square foot when you pour it to 1.5 inches. And that probably won't overload anybody's floor joist system. So it adds some great benefits. It adds soundproofing between floors. And some insurance companies even allow you to take money off your fire premiums because it acts as a fire barrier between floors. Now, you can use concrete instead of gypcrete, but concrete weighs about 18 to 20 pounds per square inch. And you need to make sure that your subfloor and joist systems are capable of handling that kind of weight. Now, if you make it lighter, of course, by putting plasticizers in it, that removes the thermal conduction of the flooring, so it makes it less thermally active. Now, the benefit of this, again, is it's consistent, even heat, good for remodels, since it only adds about 1.5 inches of height above the subfloor. I think one of the drawbacks would be it's an additional trade is needed, and which would account for some additional coordinating to get that done. Knobbed mats are another way that you can use with gypcrete. It makes it easier and faster to install. They come either insulated or uninsulated. So you could put it down on an existing cement floor with insulation, and then you'd have a nice thermal break between it and the concrete floor to pour your gypcrete on. It dries hard in about 90 minutes. So by the time usually you get from one end of the basement to the other side of the basement's already hard and ready for you to lay down whatever kind of flooring you want to lay right over the top of that. We also have Quick Track, which is plywood panels with a 5/16 groove down the middle of it, 7 inches on center. And these panels, about 4 feet long, have an aluminum plate on the back of them. And this aluminum plate now becomes the heat emitter. So the tubing in the slot touches the aluminum plate in the bottom of the Quick Track, and that heat spreads over the whole base of the Quick Track, giving you a very even, nice flow of heat over the whole floor, so you don't get any striping. Makes it very easy to do that. So this Quick Track is screwed to the subfloor. You snap your tubing in there, and then again, you could put your flooring right over the top immediately. Because it's only a 1/2 inch thick, it's great for remodeling. So you can use this, you only want to add a 1/2 inch of your flooring, which is about the same height as tile. That way you can add it to an existing flooring already. And it's a low mass radiant system, which means that it's really quick responding. So let's say you had a vacation home that you went up to on Fridays and you wanted it to heat up when you get there. If you had a concrete system, it would take hours for that to heat up. You'd have to heat it up starting on Thursday. But this, you could heat it up an hour or two before, and your cabin would be nice and warm by the time that you got there. So it works for all types of radiant installations there. Good news is it's a low mass, quick responding, minimum floor height. It's good for remodels, retrofit, and doesn't require another trade. You can also mount it on the wall and ceilings, which I'll talk about just in a few minutes. It does add a little bit more expense per square foot, but ease of installation and its advantages overtake those. One way, if you're up in the joist and you have access to the joist and you'd like to add radiant heat to your system, we have joist clips, joist hangers, and staple up as one options. Of the joist heating applications, joist clips and hangers or staple up will give you probably the least efficient performance, because you can see that the tubing is not actually touching the floor. So you don't get a good, now staple up it is, but only the very top part of the tubing is touching the floor. So it's very poor thermal contact. And generally what that translates into is extremely or much higher supply water temperatures, which is going to drive your heating bills up. You want to reduce that supply water temperature wherever you can. Now, a better way to do that would be to put joist tractor aluminum plates underneath there. Now you'll see these, the tubing is, if I can close in on that a little bit, like that, you'll see that these plates, the tubing is touching all over the sides of the aluminum plates, so you get much greater thermal transfer back to your flooring, and it covers the whole floor. So if I were to look at that from a thermograph, if I was to take a look, the drawing on the left shows staple up, the drawing on the right shows aluminum plates, and you can see the staple up, the only actual place that's actually heating up is where the staples are, whereas the aluminum tracks is spreading the heat evenly over the flooring, which will make sure you don't get striping where one part of the floor feels warmer than another part. And you'll be able to lower your supply water temperature. So in a period of 4 or 5 years, these plates generally pay for themselves because I can reduce the supply water temperature. Now, one of the real benefits to radiant heating is, let's say I can't have access to the floor. I don't want to tear the flooring up. I really like the covering. I can put the radiant in the ceiling. I can use aluminum plates mounted up in the ceiling, either over the existing sheetrock, or I can take the sheetrock off and put some furring strips and put those in there and then put the sheetrock over that again. So I can use quick track up in the ceilings to do the same thing. That's going to give you an option to have radiant heating where you couldn't have it without tearing up your really nice floors. Another good place to put this, let's say you wanted to add radiant ceiling to an existing garage that already has a concrete floor laid down. This, you could put the radiant ceiling up there, put some glycol in the water because you don't want it to freeze up, and connect it up to a instantaneous heater as an example, or an electric heater. So you've got radiant heating in your garage and a very easy installation to do that. So these all provide excellent ways to have radiant heating. I can put the radiant heating on the walls as well. Most of you know what it's like to stand next to a plate glass window in the middle of winter. You can feel that cold right there on your arm. Even though if you were to measure the room temperature, it's very much the same, but it's your body is giving up all that thermal energy to the plate glass window, and you feel colder. Well, this radiant next to a plate glass window will remove that again. So you get great thermal comfort by providing that type of option. How about a wraparound for that shower surround that you have? I know for me, stepping out of a hot shower onto a bare tile floor is an exercise in pain management and mind control. You have to mentally prepare yourself for that first step onto the tile. It makes my knees weak just thinking about that cold floor. So if I put these tracks behind it and put my cement board over it, put my tile over that, it's like taking a shower in a cocoon. It's so nice and warm on all sides. It's bathing you in radiant heat from all sides. It's a genuinely magnificent experience. How about if I took some of that tubing and put it behind the mirror in the bathroom to keep it from fogging up? Or how about if I ran a loop of tubing through a towel bar? Now I have a heated towel bar. These are just some of the things that you could do with radiant heating that you can't do with other types of heating systems. How about running it under that concrete or your granite countertop? You know how cold those are in the wintertime. You lean on them, they're just, if you've got you know the touch you get from those is extremely cold, so that makes it feel really warm because it makes the granite countertop now becomes a heat emitter, part of your heating system. Oh, it's great. Underneath, you want to do some floor conditioning for your bathroom. You notice I keep the tubing away from the wax ring. Let me just see if I can zoom in on that. Up here in the upper right-hand corner, you can see the wax ring right here. I keep the tubing away from that so that there won't be any issue of melting the wax ring from there. I could also use it for floor conditioning under a bathroom and to add that nice warm touch when you get out on a tile floor. Oh, it feels so good. How about I can use it as a radiant, just surround yourself with comfort. I can put it on the deck of the tub. I can put it on the wall behind it. All of those add to the thermal comfort that you get inside of there. And here's one where they just used the quick track panels and they're shaped like that will go around a tub and again provide that nice warm tile feeling for very little money installed. So all kinds of options going with radiant heating. Now here's one again where they put it in the shower and they warm it up before they go in there. So when they go in there, it's a nice feeling. There's no cold tiles, no any of that before. Kitchen remodeling, it works excellent as a way for if you're doing some kitchens or you want to add radiant comfort in your laundry rooms. You notice I didn't put it underneath where the cabinets are, since there's no sense in heating underneath the cabinet. I'll save that heat for just the tile floors if I want to. Now, one of the most overlooked ways of installing radiant heating, in my opinion, is radiant walls. Now, we do radiant walls because sometimes there's no room or you don't want to tear up your flooring. You have expensive wood flooring. You don't want to tear it up. You don't want to cover it up. And so putting it on the walls will give you, the comfort is almost identical. And you, because it's behind the wall and not underneath your expensive flooring, I can drive those supply water temperatures up and get some great thermal performance out of them because I'm behind the sheetrock instead of underneath your flooring, which can only handle about 87-degree temperatures at the top. Under sheetrock, I can go up to 110 degrees and drive heat through a room. Oh, it's amazing. So that's a real option. And so all I do is I cut the sheetrock out. I put the quick track up against the wall, put the tubing back in it, and then when I'm done with that, add the water. Then I can come back and put wainscoting, depending on how you pronounce it, over the front of it, and it gets it a really elegant finish. It looks professional, it looks finished, but now your wall becomes a heat emitter and just transmits that heat nicely across the floor. Now, you notice that in the drawing that I don't put the radiant heating all the way to the ceiling. Now, there's a reason for this. I always try to keep it about no more than 4 feet up, because any time after that, that's where people start hanging their pictures on the wall. And I don't know how homeowners know this, but they have the uncanny ability to take a little teeny nail and for some reason find the exact spot in the wall where the piping is and then drive a hole in it. Now, of course, because the nail's in the hole, it won't even show for a few months, and then the nail will rust out and water will come poking out of your sheetrock in the middle of your living room. So keep it at 4 feet, then you don't have to worry about it. Now, the benefit of radiant heating, I can use any floor covering that I want to. I can use carpeting with padding. I can use tile. I can use wood. Any of the things that you would normally tile a floor with, these are floor covering that you'd like to select. Any of them can be used on radiant heating. I would remind you, though, that if you're going to put carpeting down on the floor, you're going to have to drive the supply water temperatures up pretty high, because carpeting has a pretty good thermal insulative value, and the heat would have to drive its way through that. Remember, heat always takes the path of least resistance. So there's an opportunity. This is what we're talking about in a few minutes, of the difference between flooring options when we're doing radiant heating. This is going to add to our indoor environment quality. I'll talk about that just in a minute. So as we talk about these efficiencies of radiant heating, I just want to touch on this, that radiant heating is more of the types of heating systems, is a more efficient system than your typical HVAC system. So let's take a look at forced air, which is probably the dominant type of installation method today of heating. Let's compare these two. Now let's take a look at the heating part first. Forced air uses the least practical and the least inefficient thing, the most inefficient thing for moving heat, air. You end up with stratification because hot air rises. You end up with temperature drifts because the air movement in the room is drifting the temperature all over. You have noisy fans. As for ventilation, the only ventilation, unless you've installed an HRV, a heat recovery ventilator, the only ventilation you'll probably have are bathroom and kitchen exhaust fans, and that won't take care of pollens and dust and mold and particulates as it's shooting these around your house. Now, you'll see in there's an air filter in here, so I'll show you that. Close in on that air filter just a bit. The air filter that comes with, if you have one of those disposable fiberglass filters that's in your furnace right there, they don't meet a single healthcare facility standard, not a single one. They'll filter, they will filter dirt and dust, but not any of the microbial issues or harmful gases issues. Now, there was a Professor Tang of the University of Calgary says this: these air filters protect the health of the blower motor, not the body. So if you're, and now HEPA filters are another thing, but even they aren't good at getting all the microbials out of the air. And they do demand that you take care of them quite a bit more. Now, if we compare that to a radiant heating system, I don't have the fans blowing air all over. I don't have the filtration system. Instead, I'll have a HRV, a heat recovery ventilator that will provide air changes in the house, meaning I'll get a clean, dehumidified air back into the house and ready for me to use again. And I also want to talk just for a minute. Water can hold 3,500 times the amount of heat as the same volume of air. 3,500. So what that means, the 3/4 inch pipe that you see up there carries exactly the same amount of heat as an 8x14 duct, without all the heat loss associated with duct loss as well. Now, to show you the math behind that, I hate to drive this, make you a mathematician here just for a minute. But water has a specific heat of 1. That means one BTU is equal to 1 pound of water raised 1 degree Fahrenheit. The specific heat of air is only 0.24. So the density of in pounds per cubic foot of water is 62.4 compared to the density of air is 0.074. When you multiply those together, 1 times 62.4 gives you an energy transport capability of 62.4 BTUs per cubic foot per degree, compared to air, which will only give you 0.018 BTUs per cubic foot per degree. If you divide 62.4 by 0.018, you get 3466 or 3,500 times, which means to project the same exact amount of heat through the home, I'm going to have to move air about 5 or 6 times more fan power to get that air to move than a pump would use to get the same amount of water to use. And even according to the Department of Energy, they say radiant heating has a number of advantages. This is from the U.S. Department of Energy. It's more efficient than baseboard heating and more efficient than forced air heating because it eliminates duct losses. People with allergies often prefer radiant heat because it doesn't distribute allergens like forced air systems can, and it uses much less electricity. So how do I know how much heat does my house need? In order to do that, you need this figure, BTUs per hour per square foot. You have to determine how many BTUs per hour per square foot are released so that I have to have a furnace and heating system that will replace that amount of heat. And to do that, you have to do what's called a heat loss. I don't care who you are, that's still funny. Now, heat losses can be done on the internet. You can look up how to do heat losses. You can go on to Uponor. There's a free program called LoopCAD that gives you on a 30-day free trial that will calculate your heat loss in your home. And also, if you'll draw in the flooring plans, we'll also draw the tubing out for you as well. So those are some, I don't have enough time on this particular webinar to talk about it, but it's a great way to find out how much heat do I need. And I'll tell you, you'll find out most of the time your houses today are way overheated. Now let's take this and I'll start moving into the comfort area just a little bit. Now, comfort you'd think would be kind of a subjective thing. However, the American Society of Heating, Refrigeration, and Air Conditioning Engineers, or ASHRAE, has come up with standards of comfort that make it go from the subjective to the objective. That way there's measurable ways to determine if an environment is going to be thermally comfortable for human occupancy. And so let's start with a definition of comfort to begin with. John Siegenthaler has one of the best examples of that, of how to measure comfort, is controlling the rate and manner in which the body loses heat. Now, what does that mean? Take a look at this thermograph before you. The red shows energy in the form of heat. Every human being produces about 500 BTUs per hour when you're just sitting there. 100 of those BTUs are needed for metabolism, and the other 400 BTUs are constantly being shed away. And how fast you shed them determines your comfort level. The slower the BTUs are shed, the warmer you feel. The faster they're being shed, the colder you feel. So I want to get away from the understanding that we don't absorb heat. Only cold-blooded animals do that. We are always producing heat. So it's not BTUs is not the issue for thermal comfort. I'm making my own already. I don't need more BTUs. I need comfort. I'm the manufacturer of BTUs. I'm an actual net exporter of BTUs. I just need some help controlling the rate that I'm exporting these BTUs, which drives us to the ideal heating curve. This is a study done back in the 1950s by the Department of Energy in Bell and Gossett. It is still valid to these days. They took thousands of people and measured what made them thermally comfortable in an environment. And they came up with what's called the ideal heating curve. So down at the bottom where your feet are, we'd like to have a temperature of around 73 degrees, somewhere in there. And up where your heart is, it needs to be about 65 degrees. And you notice that it drops off as it goes up. That's because nobody lives up there, so they didn't have any data for it. And so, again, this represents what over 97% of the people would feel comfortable in an environment just like this one. Now, if we match these two, if we compare a forced air heating system on the left with the radiant heating on the right, what I want to do is demonstrate the ideal heating curve is the black line that you see on the forced air side, and then the actual measured temperature is the blue line that you see there. So you can see that the lines are not touching each other. Now here's the thing with that. The wider those two lines are apart, two things are happening. Number one, you're wasting money, and number two, you're not thermally comfortable. And the wider it is, the worse it is for you. And so you can see that because hot air rises, it comes into the room and it goes right up to the top of the ceiling. You can see up there at the ceiling, it's about 90 degrees up there by the ceiling. But my feet down here are like 63 degrees. Now, you all know, if you've been out ice skating in the middle of winter, you can stay out skating all day long until your feet get cold, and then it's no more fun anymore. That's because your feet are the ones that do most of the determining for your thermal comfort. And of course, if my hot air is all up at the ceiling, I don't have my heat where I need it. So to get it back, what I'll do, I'll put a ceiling fan in there to shoot the heat back down to the floor. So now I've just introduced a draft to get my own heat back. Now that doesn't make much sense anywhere. As compared to the other part of that as well is, look at this temperature up on the roof up there. It's 10 degrees outside. My roof is at 90 degrees. That means there's an 80 degree delta T, which means a lot of heat, the 80 degree temperature difference. A lot of heat is going to be escaping out from that roof. If I make that same comparison to the radiant on the right, you'll see that the radiant heating curve almost identically matches the ideal heating curve. And especially down to the part on the floor where your feet are nice and toasty. And once your feet are warm, you tend to be more comfortable. And again, up on the roof now, my temperature up there is only in the 50 degrees. So now I only have a 40 degree temperature difference. So I'm losing much, much less heat out the ceiling than I would be from just a forced air system. This graph here is designed to show you, most people think you lose most of your heat out of your head, which is simply not true. You have two of the largest arteries in your whole body supply fresh, warm blood to your head, your carotid arteries. So they're getting tons of heat all the time. It's your left and right foot and your left and right hand that most of this discomfort comes from. And of course, that's directly affected by hot air rising, your thermal comfort in a living room or bedroom, for example. And again, you can see that out of the vent in the floor, I've got about 110 degrees coming out of the floor. Hot air rises, and now the cold air begins to sink once it's up on the ceiling. And now look at the temperature where your flooring is. At 63 degrees where my feet are, where the chair is at 68 degrees, which is, it's a lot of uncomfortable, uneven all the way. You can see there's a temperature difference from one side of the room to the other. Those are called asymmetrical temperatures. Compared to the radiant on the right, which has a nice even floor temperature, midsection where you want it, about 65 degrees where your heart is. And of course, I don't want any temperature up at the ceiling because nobody lives up there. So unless they're paying rent up there, I just want to keep that as cool as I possibly can. So I'm going to ask you this question. What does every house with forced air heat have in common? Every house with forced air heat. What do they have in common? Every house with forced air heat. A blanket on the couch. Every single forced air house I've ever been in has a blanket on the couch. Why? Because my hot air is up at the ceiling and I'm sitting in the cold air. And now that the cold air is sitting with the couch gets cold and I need a blanket to keep me warm. You shouldn't have to do that in a thermal environment made for comfort and not to satisfy the thermostat. If we get away from satisfying the thermostat to satisfying the person, we'd have a whole different way of measuring thermal comfort in a home. Just to ask you, how many thermostats are in your house if you have forced air? Now, my wife and I built our house back in the 70s and didn't have radiant heating, wasn't available then. So we have one thermostat and it's located in the hallway where nobody lives. My car has 3 thermostats, 3. One in the passenger side, one in the driver's side, and one in the back seat. My house has 1. So we have a 3-story house. So I don't know how you folks are with forced air, but my wife and I migrate twice a year, just like wildebeest. In the summer, it's too hot upstairs, so we migrate down to the basement, take everything with us. Then in the winter, it gets too cold in the basement. We migrate everything back upstairs all the way up to the upper floor. Twice a year, just like wildebeest, we migrate back and forth. Now, your heating system shouldn't do that. Your heating system, it should be a comfort package that allows you to be comfortable anywhere, anytime. All right, so we've talked a little about radiant heating and all that. Let's go into the indoor environment quality. This is why many of you have tuned in today. So let me ask you, is our house making us sick? The things that are, as they tighten up houses more and more and more and trap all of these volatile organic compounds inside of our houses, what's happening to the indoor environment? And to do that, I want to show you this, a little animation of, we have several parts make up indoor environment quality. First one is indoor air quality. Now, indoor air quality is made up of, particularly if you have VOCs or volatile organic compounds like formaldehydes. When they make cabinets, typically the glues have formaldehydes, paints, adhesives, solvents, propellants, cleaning supplies, ammonia, for example. Each one of these add to the indoor air quality that you're breathing in all of the time. And tighter houses make that exacerbated even more. On top of that, we have microbial contaminants such as mold, bacteria, Legionella. And then we have gases as well, such as carbon monoxide and radon. And if you have a house built in clay, you need to get a check for radon. Pesticides, glues, asbestos, all of these things make up what's called indoor air quality. The next is indoor comfort quality. This is made up of relative humidity, asymmetrical temperatures, differences in temperatures across the room, stratification where heat rises, temperature drift where moving air makes different temperatures around the room. Your own metabolic rate makes a difference in this too. And then as well as that, something called surface temperatures come in to do this, because if your furniture is cold, you dump BTUs from you into it through radiant heating. I don't know that you even knew that. So here's what happens. I could be quite comfortable in a basement with indoor comfort quality in the summertime being nice and cool, but if there's radon leaching in through the indoor air quality, then it's dangerous. So you have to take all the parts, all the pieces in the puzzle to make sure you have a home that's not making you sick to begin with. Next one is indoor sound quality, fan noises, air velocity, vibration from equipments, for example, humming noises that you hear. Outdoor noises transmitted through the thin glass makes a difference too. And one of the ones that most people don't even know about is called indoor light quality. Now, the National Research Council says, indicated there's an effect of indoor lighting on performance via the effects of lighting on your circadian system, which influences depression. And you can get syndromes like seasonally adjusted disorder or SAD disorder, and it could interrupt your sleep pattern based on the light that's in your home. So these are becoming more and more understood as we test out more and more of these systems. And then finally, the fifth piece of the puzzle is indoor odor quality, and especially paint or cooking odors. Any of you who've cooked lutefisk down in the basement, down in the kitchen, I mean, no, it's not going to be a pleasant evening in the bedroom that night. So those odors can be, and they're measured by intensity and persistency. And again, they're combined with air filtration performance that might be helping you or not helping you at all. And so indoor odor qualities is the fifth piece of that puzzle. And when you put those all together, you get what's called indoor environment quality. Now, the air quality itself, what makes up indoor comfort quality? We'll pick those. Number one is your metabolic rate, how fast you burn off BTUs. Each person's a little bit different. And so two people in the same room might not be comfortable with the same temperature. The clothing that you're wearing at the time affects your indoor comfort quality as well. Any drafts that are coming through, for example, if your curtains are standing out at a 30-degree angle because of the cracks in the windows, that's going to affect the thermal performance of your house and your comfort quality. The temperature drift, how far is your thermostat set to drift from on to off? Some of those are as much as 3 or 4 or 5 degrees, and they can affect your thermal comfort performance. On top of that, we have stratification, hot air rises, and we have to put fans on to capture that heat back to the floor where our feet are. And then surface temperatures and mean radiant temperatures are the same thing. And we put those together with what's called dry bulb temperature. That's the actual air temperature. So mean radiant temperature and dry bulb temperature together produce one called operative temperature, which is the only accurate way to measure indoor thermal comfort because it takes into account temperatures of room surfaces as well as air temperatures, and then divide by 2 to get the average of those. Asymmetrical temperatures, let's say you have a plate glass window on one side of the living room. That temperature is not going to be the same there as everywhere else in the room. And then you can have another one called relative humidity, where that can affect, in the wintertime, furnaces dry out the air so much. You know those sparks you can shoot from your fingers and them rubbing your feet across the carpeting. And then finally, there's the last one called ramp up. How long does it take from the time your furnace calls until it satisfies the thermostat? And those make up, if it's too wide, you'll get temperature drifts, and that affects the whole thing. So when you put those together, you end up with a good thermal comfort. And this is what we're trying to shoot for in a home. As far as the indoor air quality goes, we're going to talk just a bit of biological matters and particulate matters that are entrained in houses today that you might not even be aware that you have them. And understanding them will maybe help you feel, boy, I don't know where my nose is running all the time. And volatile organic compounds, we've talked a little bit about those. So much of what we do has chemical propellants in it or odors that are off-gassing. Buy new furniture, for example. It takes 6 months for the glues inside of new furniture to off-gas. And guess where they're going? They're going right into your lungs. And so having fresh air and repeated fresh air is super important. Gases and vapors are extremely important. So let me point one thing that you might not know. Dead skin cells. I don't know if you knew this or not, but every human being sheds 1.5 million dead skin cells every hour per person. 1.5 million dead skin cells. Where do you think they go? They go on to the carpeting, they go on, they're transported through the air, through the furnace system, back on. I know what, here's something you might remember that can point this out. Do you remember when you start your furnace up in the fall? Do you remember that smell you get when you first fire up your furnace? Do you know what that smell is? That's your dead skin cells on top of the heat exchanger being burned. That's where that comes from, because your filter didn't stop them from being there. So it turns out your Uncle Harry, the last time he was over, left a couple of 100,000 dead skin cells, and that's what you smell when you fire up that furnace in the fall. Now, the good news is dust mites eat them. So your carpeting has dust mites. Now, dust mites produce about 200 times their body weight in waste every day. Guess where that goes? And they hide way deep in your carpeting, in your furniture. And regular cleaning is no match for these either, because they have little teeny claws that pull right into the fabric and hold on. So 95% remain even after vacuuming. I think the only way you can actually get rid of them is steam cleaning. So you'd have to check that out on your own. So half of a teaspoon of dust may contain over 1,000 dust mites. And these, of course, have a 2-week lifespan, and then they die. So these hatch, reproduce, and die within about 3 weeks. An average of 10,000 live dust mites are typically found in 10 square feet of carpeting. Now, in this same area, 10 square feet, there's approximately 100,000 dust mite corpses decomposing in the carpeting. Now, I'm not trying to scare anybody or anything, but you're wondering why you're having allergies inside of your home. That's why. And the reason that we put carpeting in is because our feet are cold. If we had warm feet on nice wood floors, we could solve so many of these problems. So if you're ever looking for something to do on a Saturday, go on YouTube and type "what's crawling in my carpet." And here's some of the things that you'll get. This is what's crawling in your carpet. Now, the good news is dust mites are really, really, really small, microscopic. The bad news is dust mites are really, really small, microscopic. So you can't see them, but they're there, they're living, they're dying, and they're decomposing in your carpet. And if we're going to talk about indoor environment quality and how ways you can improve that, remember, carpeting doubles its weight every 7 years. I don't care what you do to it. So cleaning is not even the issue. It's just the way carpeting retains molecules, moisture. Fleas are another one. There's 2,500 species of fleas, and each one of them is able to jump 50 times their body length. And they come in on your dogs and cats and may live in your home. Same problem there. Again, we have bacteria growing all over in carpeting. 1 square inch of carpeting can harbor as many as 200,000 bacteria. Many of these viruses can survive weeks in carpeting, way, way longer than on wood or tile surfaces. Salmonella, for example, has been shown to survive in carpeting for up to 1 month. The flu virus is especially speculated to survive multiple days in carpeting, even with cleaning. So a doctor named Philip Tierno, he's a microbiologist and immunologist at New York University, wrote a book, The Secret Life of Germs. He found in his research that your carpeting probably contains 200,000 bacteria per square inch, making it 4,000 times dirtier than your toilet seat. And so vacuuming alone is not effective in removing skin cells, food particles, and pollen that these bacteria feed on. So we have all these issues. And then we have the issue of pollen in the home and how that's held on and in carpeting, as well as mold, which can do some serious, serious lung damage. So again, in the whole, I hope what we've seen over this is the outlook of indoor environment quality is affected very much by your heating system, by whichever heating system you pick, and what flooring materials you pick help determine your actual indoor environment quality. And we don't want our homes to be making us sick. We want our homes to be making us comfortable. We want our homes to be making us healthy. And we want our homes to be making us more energy efficient and less reliant on energy sources outside of the US. And so hardwood floors are just a healthier solution. So in wrapping up, I just wanted to say we've taken a look at an overview of radiant floor heating systems and how these efficiencies of radiant heating over 4 stairs, an example. We talked a little bit about human thermal comfort and what impacts that and how each heating system plays a part in your human thermal comfort, and finally how radiant heating improves the indoor environment. And I hope you've come away understanding radiant heating really does help a home's indoor air quality and indoor environment quality. So I'll throw it back to you, Mark, to see if you've got any questions.
Yes, Steve, we do. We have a lot of questions, and thank you very much for that presentation. I'm hungry now. I'm just kidding, but we do have wonderful, wonderful questions from our audience. I want to start off with a question from Ulrich, and Ulrich's question is: do those methods work for radiant cooling, especially in ceilings and in walls, not so much floors?
That is an absolutely excellent question. Commercially, radiant cooling is really coming into its own for the very reasons that we've just talked about so far. Engineers are working on indoor environment qualities. Radiant cooling does exactly the same thing. It's 3,500 times better at removing heat. The indoor thermal performance is way better. The indoor temperature comfort's better in commercial. So I don't think there's a Walmart built today that doesn't have radiant cooling in it, or a Hilton hotel. I could be wrong, but I think they're all built with radiant cooling. And the thing is, radiant cooling hasn't worked its way down to homes yet. Now, the bigger homes do have it. Some of the 20 or 30,000 square foot castles that some people have do have radiant cooling in them. And it'd be a great subject to go over one day down in the future if there's a need for it, to just have a really good discussion about radiant cooling and is it a possibility. Now it is, the only thing is you have to remember radiant cooling will not remove the humidity. So you still have to find a way to dehumidify the environment apart from the cooling. It'll only do it won't do the latent heat, which is the humidity in the air. It'll only do the measurable heat, or the sensible heat. So that's a hard way to answer that, but in a short time, it's not generally feasible for a 3,000 square foot house right now. It's doable, but it'd be a little bit on the expensive side.
Along the same lines about the radiant cooling, Ali had a question about how well will radiant cooling work in a hot climate?
We just one of the largest radiant cooling jobs ever done was in one of the warmest environments in the world. They did the airport in what country was it? Thailand. They did the airport in Thailand with radiant cooling. Now, the average temperature there was, I think, 88 degrees, and the humidity was just about as bad. They're still saving at least 37% over their existing efficiency of their existing cool air system that they were going to install. So yes, it does work, and yes, it does work effectively.
Okay. We had a question from Trudy. She wanted to know, is radiant heat practical in an off-grid home?
Well, there you are. That's a good, well, here's the best answer of all. You can hitch a radiant heat up to a wood stove, and you'll get, the only thing you have to provide electricity for is a little teeny pump that draws probably 30 watts, which is about 6 Christmas tree bulbs. So you can get 30 watts would do an average home of about 2,000 square feet with enough pumping to run a radiant heating system with a wood stove. I don't think you can get better thermal performance on any off-grid than that. It ranks right up there with solar, and it's not nearly as expensive to install or maintain.
We had a question from Lynn, and the question is, considering the temperature increases associated with climate change, can cold water be run through the system to cool indoor spaces? So it kind of touches on that radiant cooling topic we were hitting on earlier, but I just want to make sure to cover Lynn's question.
Yeah, that's another outstanding question. And again, that's what geothermal heat pumps are doing even today. They're drawing cooler water from wells deep in the earth, and they're using that to cool homes on the inside with a fan coil unit and connecting it up or to a radiant cooling system. And so they use a little heat pump connected to that. It'll make heat in the winter and cooling in the summer, but because it's drawing cooled water from 200 feet down or in the well, it provides almost free cooling in the summertime. Literally, because all you're doing is running it through a fan coil and pumping the water back into the earth again. That's a great question.
We had another question from Ulrich, though, and I thought this was really interesting. Are there SIPs that have pre-installed radiant heating or cooling systems in them?
I'm trying to think. I know they're researching them. I'm trying to think if I know where there's one done somewhere. But I'm racking my mind. I can't think of one that I know of. Nope, I don't
think you could do. I mean, it's something you could kind of retrofit in or maybe add on in the construction process.
Oh, sure.
Is that something that could happen for sure? Okay.
Yeah, they could panelize it, and then when the panel comes back, you just connect the tubing up to a manifold, just like you would any other time. So, right. I'm trying to think if I've seen it done. I just can't think of one. Well, you may have a business started there, sir.
Well, we do.
Come and see me if you get that running, would you? By the way.
Well, I know SIPA is a friend of Green Builder Media, so if any of them are listening, maybe they can either chime in with us or hunt down that kind of technology or pursue it if it isn't existing now. So, thank you for the question, Ulrich. I had a question from Aaron. Is it better to use a hydronic system versus electric? The question is really in regards to maintenance and operational costs.
Yeah. Okay. So there again, it depends on your electricity costs. Right now, people say, well, electricity is 100% efficient. If you put 10 watts out, if you put 10 watts into it, you get 10 watts of heating out, which is true. The problem is you get probably 40 to 50% transmission loss coming from the generator, wherever it's generated, to your home. So electricity is not 100%. I mean, if you're talking environmentally, isn't always the best solution. However, in a home, they work really well. The problem is electricity is usually fairly expensive. So you, like if you're paying probably 9 or 10 or 11 cents per kilowatt hour, if that's your price range for your electricity, that will cost you about 3 times as much as the same cost for natural gas heating to produce the same BTUs. So right now, if you live up in the Washington area, state of Washington, where the Columbia River system is, and electricity is like 5 cents a kilowatt hour, then I'd do that in a minute because it's really cheap to run.
Well, I think if I can add a little bit of context of my own to Aaron's question, Steve, we're seeing in the code, in the energy code, that there's a movement towards electrification and moving away from natural gas and heating that way and using that and the carbon footprint associated with that. So I wanted to make sure to add that a little bit of context. And that was not Aaron's, that's my own, just seeing the trend in some of the building codes.
It sure is. And I think we'll see more and more of it as they try to cut down on carbon emissions. Coming from any fossil fuel is going to produce carbon emissions. That's true. The issue is what we've done is if the problem that we have is most of our heating that produce electricity run on natural gas or coal. Well, all you've done is move the carbon footprint from inside the house to some facility 50 miles away. We have to figure that out.
Yeah.
And then so we could actually truly drop carbon emissions, like windmills or solar, something like that.
Right, and batteries too. The solar works well, but the battery component needs to be a part of that.
Exactly.
So we have a question from Carol. She wanted to know what installation system would be used for under-counter heating, and would that be a reasonable heating for a great room situation, or would the counters get too hot?
Again, I can put any supply water temperature I want through them. So that's easily manipulated. And we put one at our factory where our showroom is, underneath the counter where the guests come in. And it's just nice. All it does is take the chill off from the countertop. It's a concrete poured countertop with a quick track underneath it, 5/16" tubing, connected up to a little teeny heater underneath the sink. And it pumps some warm air or warm water through that and keeps it really nice to the touch. It's really kind of clever. And it's just one of those things that adds thermal comfort to your home. Makes it a little different than everyone else's and actually a little nicer, I think. Now just think about it. In the summertime, if you could run cold water through there, you could keep your beer cold sitting right on top of your countertop. Wouldn't that be nice?
Nice. Well, you talk a little bit about versatility and flexibility, Steve, and I had a question of my own. When you have a radiant system, that means no floor vents, correct? Because if that's correct, that really opens up some space when it comes to interior design, furniture placement, that sort of thing.
Oh, it is. Yep. I got my wife and I got in big trouble with my wife one time because I couldn't put this countertop or this curio cabinet that she bought where she wanted it, because it was right in front of her where one of the vents were. So I had to go readapt her curio cabinet, and I got in a lot of trouble for that. So just saying, if you want to keep your marriage right, get rid of those vents.
Nice. A couple questions from Keith. We're going to start with this one because Keith is designing a new house.
Well done, Keith.
And he's going to have a 4-inch slab on grade. And he received 2 quotes. One was for a 1/2-inch PEX, and the other was for 7/8-inch extra large PEX. He's trying to figure out what are the differences between the 2 applications, especially when it comes to the 7/8 inch.
Boy, I've never seen. I'm sure it's 7/8-inch pipe because I didn't know there was a 7/8-inch pipe. There's a 5/8-inch pipe and a 3/4-inch pipe and a 1-inch pipe. That's an awfully big pipe to be running in concrete, and I don't know that it would. All it would do is cut down on your how hard your pump pumps, because the bigger the pipe, the less hard your pump has to work to get the same amount of BTUs through.
Well, and let's say that he typed it in wrong and he meant 5/8 instead of 7/8. What's going to be the difference between a 1/2-inch versus 5/8?
Oh, okay. So you'll use 5/8-inch tubing when you want a really lot of thermal output, like a snow melt system, for example. The bigger the pipe I make, the more BTUs it's capable of carrying. So for a snow melt, I'm going to need 5/8. For an indoor radiant system, I can use 5/8, and I'll save a little bit of money by dropping my supply water temperature. But I don't know that the cost of the difference in the tubing would justify it for an indoor environment just with radiant floor in the concrete, especially if it's insulated under the slab.
Okay.
If they've not insulated it under the slab, then I go with the 5/8 tubing if it's available.
And then his second question was if you had any opinion on using open source domestic water. So this is used for both the floor heating and the house water source via a heat pump water heater. And he's got one in mind from Sandon. But can you talk a little bit about open source domestic water and a heat pump water heater?
Yep, they have Again, codes are, you have to check with your code to make sure you can do this, but some communities will allow you to use your water flowing through your domestic hot water tank to go through your radiant system. Now, that most won't allow that. Like Minnesota, you can't do that. So you might have to have a heat exchanger between the domestic hot water and your potable water and your boiler non-potable water, or your heat exchanger non-potable water. However, if your community does allow it, there's another option you might think of called a combi boiler. It heats your domestic hot water and your boiler separate from each other in the same cylinder, in the same tank. So now you only have one chimney, you have one stack, you have one appliance, and it'll do both the domestic hot water and your radiant heating with two separate systems inside of the same storage tank. That's one, but he's talking about is just an open source using potable water through a radiant heating system. You have to check code though. I'm not sure every place can do that.
Okay. I had a question from Mohammed. He wanted to know, can you use radiant heating in a wood frame structure that has 2 floors? So it'd be like a 2-story home.
Well, yeah, Mohammed, I think if I have this right, so you have a slab on grade maybe in the basement and then a joist heating above that. Yep, you could do that. We can do 4 or 5-story homes all the time with all kinds of different applications. Some wood panels or quick track panels in there, some joist track panels, some slab applications, and some gypcrete, all in the same house. It's easily done too. Great question, Mohammed.
I wanted to send out a final call for questions to our audience. Thank you, Steve, for sticking around a little bit longer to get to people's questions. We have a question from Elizabeth on the radiant ceilings. She wants to know, how does the heat get down low enough to fully heat the room?
Oh, that's a great question. We're starting. Elizabeth, aren't we so used to thinking the same way that, see, the thing about radiant heating is when the radiant comes off from wherever the heat emitter is, whether it's in the floor or in the ceiling, it gives up 0 of its energy until it hits something. So when that thing starts out at the roof, up the ceiling, if there's nothing between it and the floor, 100% of that energy is going to go right into the floor again. You see, it gives up none in between, unless it hits something, and then it heats it up. Isn't that, it's kind of hard to wrap your head around it, and I understand what you're asking, but the truth is, it's not like air that's constantly giving up its heat as it goes along. So the farther away you are, the less heat it has in it. This isn't true with electromagnetic waves. No energy is given up until it strikes an opaque object. Then it gives up all of its energy at once in the form of heat. That's pretty cool. No, that's pretty warm, actually. So I got mixed my metaphors there.
So I don't see any more questions, Steve. I have one question myself as a former concrete finisher. I might have missed it early in the presentation. What thickness is the slab if you're doing radiant and you also have rebar in that slab?
Again, it'll depend on the coating, but most homes are 4-inch with rebar.
Yeah.
And you can attach the tubing right to the rebar and then just pour the cement.
Oh, okay. Okay.
Yep. Pour the cement right over it. Works good.
Oh, actually, we do have another late question from Trudy. Wants to know, in a 2-story home, would you only need to heat the floor between? So I'm guessing she's asking about, it's got a basement and it's got a main floor and an upper level. So you want to take this, Steve?
Sure, I do. Trudy, I love that question. I actually wait for it to come up because it's first of all, it shows you're really listening in and you're figuring out that, hey, I can do one heat source, will do both sides of it. In theory, that could work. I could put radiant flooring on one side of it and put radiant ceiling on the other side of it, and that's all my heat would be trapped between the 2 floors. So yes, you can do that. For better thermal performance, though, it's probably better because remember, heat will always take the path of least resistance. So these heat sources need to not have any resistance between them and where they want the heat to go. And so insulation might be a problem between them, but yes, it can be done. And I've seen it. They put radiant ceilings in one and radiant floor above it. Works fine.
All right. One last question, right under the wire. I was just about to wrap it up, but we got a question from Ali. Can the radiant heating be integrated with the slab concrete foundation? And the answer, of course, is yes, it can.
Absolutely. It's made for that. That's its best thermal performance comes when it's buried in cement. High mass, slow responding, very even, very cost effective. I can have supply water temperatures in the middle 80s to heat my middle 80s. That's about 8 degrees less than your shower to heat your whole house in the dead of winter, even here in Minnesota. That's incredible, incredible performance.
Well, I don't see any other questions, Steve, so I want to thank you again for coming back on. This is your fourth time, and it's always a good time to have you here. So thank you, sir, for joining us today.
Thank you so much. Be safe, everyone.
Thank you also to our audience for attending and asking all those wonderful questions. We got to them all. I also want to thank Uponor for their sponsorship of today's webinar. We're going to take a little break from the webinar series, but stay tuned to your emails for announcements on future Green Building Media webinars. In the meantime, I hope you get out and enjoy all that fall has to offer. Until we meet again, take care, everyone.